Today we have a short topic, and it's a natural extension of Calculus 1. I don't think you'll find it too hard, except that the review entails a lot of graphs and things like that, and recollections of different functions that maybe you haven't seen in a while. So you might take a look back at your section on quadratic surfaces, spheres, and planes. We're going to be sketching those, reminding ourselves how to sketch those. This is kind of a trick section. It looks so short and easy, but it's actually demanding that you go back and recall all those things that you did before, because we're going to be doing calculus with those things this semester. All right, so here's a concept from Calculus 1, and what we're about here is doing Calculus 1 in more variables, so it's multivariate calculus this semester. Calculus 1, you can have a function y equals f of x of one variable x, and get out one output y, and we said a function is just a rule that assigns to each input in some set of allowed inputs called the domain exactly one output from a set called the codomain, a set of allowed outputs. And then what outputs actually occur are called the range. So here's the square root function, and we'll say this: when we have a function that you input numbers and get out numbers, then we can graph it in the plane. In general, maybe you can input x as a fruit, so the domain is the set of all fruits, and you output some present, so the codomain is the set of all presents, and then the presents actually come out when you put in a fruit, are the range. Here, since we're dealing with functions of a number getting out a number, input a real number, getting out a real number, we'll call it a real valued function of a real variable. What numbers can we put into the square root function? We can't take the square root of a negative, but we can take the square root of any other number. So we say the domain is all x greater than or equal to 0. We don't need this less than infinity if we don't want. And then what's the codomain? We'll say, oh, it's a real valued function, so the codomain might be the real numbers. Or it can be any set that includes all numbers that actually do come out. The range, what can I get out? I can get out any non-negative number, right? If I want to get out 2.7, I just put the square of 2.7 in, and I get out 2.7 for y. If I want to get 3.8, I put in the square of 3.8, and I get that out. So I can get out as y any non-negative real number I want. So we'll say the domain is all y greater than or equal to 0. And that's what we did. And then we said for a real valued function of a real number, we could sketch it by drawing the x-y coordinate system. Here's x and y. And you just plot all the points, x followed by f of x, right? All x, y such that y equals f of x. And that's what this one looks like when you plot all those points. You can't plot an infinite number of points by hand, but you can try and draw a smooth curve with your pencil. So there's what the sketch looked like. How shall we extend that now to functions of more than one variable? Well, a function we said in general is just a rule that assigns to each input x exactly one output y. What we'll do for a function of two variables, we'll say f of xy is a function of two variables, and we can write z equals f of xy if we want. If for each ordered pair xy, we get out exactly one number z. So it's still a function, still a rule that to each input assigns exactly one output, but the inputs are ordered pairs x, y. And we'll only be interested in ordered pairs of numbers x, y, and real numbers output z. That means we can make a sketch of a function of two variables in x, y, z space. Remember how to draw these? Y and z in the plane of the board, x coming out of the board. And the idea is you want to have a right-handed coordinate system, meaning that if you don't have to. There are Russian aircraft that use left-handed coordinate systems, for instance, but it's rare. In math books, you'll always see a right-handed system. Meaning if you put your right hand pointing in the direction of the x-axis, and you turn your right hand towards the y-axis, your thumb of your right hand will point in the direction of the z-axis. If you did with your left hand, right, you point in the wrong direction. So we'll draw our coordinate systems right-handed, with y and z in the plane of the board, and x coming out of the board in the right-handed system. And then we'll say, suppose we want to sketch this function, for instance, f of xy equals x squared plus y squared, also known as z equals x squared plus y squared. Well, we've actually sketched some of these before, if you think about it. Remember the quadratic surfaces. That's what this is. One of the quadratic surfaces was an elliptic paraboloid, and in this case, right, you could put z equals x squared over a squared plus y squared over b squared. It was an elliptic parabola. That's why I say it's a deceptive section. It makes you go back and review a bunch. And this is with x squared over 1 squared plus y squared over 1 squared is an elliptic parabola. When a and b are equal, the numbers under x and y, the squares are under x and y, then actually the ellipses degenerate to circles and you get a circular paraboloid. So here, for instance, if we take the cross section of this surface in xyz space with the plane z equals 1, then we get this circle x squared, by putting in z equals 1 here, we get what's called a trace. We put z equal a constant number, we get the trace z equals 1. Is 1 equals x squared plus y squared is a unit circle, x squared plus y squared equals 1. Is this circle in the z equals 1 plane. So you draw a unit circle here, and then you can draw traces in the other direction. Remember, if you cut it down this way, say put x equals 0, now you've got the equation z equals y squared. So within the x equals 0 plane, the yz plane, we sketch the parabola z equals y squared. And then similarly, if we put y equals 0, so that this falls out, you've got z equals x squared. It has this trace here in the xz plane. You could sketch that, make another parabola. I didn't draw it here. But the idea is if you have parabolas in this direction, parabolas in this direction, circles in this direction, then you can sort of sketch it like this and get a circular paraboloid. So a sketch of a function of two variables is actually a surface in xyz space, because for each xy in the xy plane, you plot a point up above it, z, and so over each xy you get a z, you get a surface up here, over the domain, whatever the domain is here. Well, what's the domain of this one? If it's f of xy equals x squared plus y squared, I can square any numbers, and I can add any numbers, so the domain is just all ordered pairs of real numbers. It's the whole xy plane. So in calculus 1, the domain was some subset of the real number line, because you were putting in one real number. Here you're putting in ordered pairs of numbers, points from the xy plane, so your domain is a plane region. Assuming, again, you're a real valued function of an ordered pair of real variables. So for this one, we'll just say the domain is the whole plane. We'll put R2. What does that mean? It's off the end of the page. It means R Cartesian product with R. So you should see R x R here. Meaning this, remember the Cartesian product? Maybe I should point this out just briefly. The Cartesian product of two sets, let's say this set A, B, with this set, here's Cartesian product, 1, 2, 3, is the set of all ordered pairs where the first element comes from this set and the second one comes from this set. So we could say it's the set of all ordered pairs, A1, A2, A3, hope you can see it on the camera, B1, B2, B3. Two elements in this set, 3 in this set, the set of all ordered pairs, there's 2 times 3, or 6 elements. Well, for our Cartesian product, we want the whole plane. We take the real numbers, Cartesian product with the real numbers. R, Cartesian product R is often denoted R2, or R squared. Will be the whole xy plane. We'll say that's the domain, because this actually extends up forever. We just cut it off here to be able to draw part of it, to show what the important part looks like. Alright, so there's sketching a function of two variables. It's a surface in xyz space, and so this gets very fun to sketch actually later on. Here's another one. You want to be able to sketch things that you haven't seen before. How can you make a general plot? Well, actually, there's some nice software out there. If you have MATLAB, that costs money, or Octave is free from the GNU new software site. You can download that and learn how to program. We won't do that for this course. It'd take too much time away from doing calculus. But if you have those at your laptop, those are nice for for plotting these. I have a bunch of plots you'll see during the semester made in MATLAB or Octave. Suppose I want to sketch this one. You could sketch it on the computer, z equals 1 over x squared plus y squared. How can I figure out how to sketch that, which is not one of my standard surfaces that I know from previous calculus? Well, when you see an x squared plus y squared, one trick everybody knows, if you can replace that with r squared, right? Now this is z equals 1 over r squared in polar coordinates, and theta isn't present. When theta isn't present, that means there's a radial symmetry. So if you take this curve, let's plot it in the xz plane here. Z equals 1 over x squared, or I can put it 1 over y squared. Maybe I should put it like I did up here with yz. So z equals 1 over y squared, and this would be y versus z. We know how to sketch that, right? We sketched that before. It's 1 over y squared looks like that. And then, because there's radial symmetry, you take this curve in the yz plane and you rotate it around the z-axis. This function doesn't depend on theta. It means that you get the same curve no matter which theta direction you point in the xy plane. So now you put x coming out of the board, y over here. Here's your curve, z equals 1 over y squared. And you revolve it around and get this surface, and there's what z equals 1 over x squared plus y squared looks like when you try and sketch that. So you want to be able to know those couple of tricks by hand. One is to know your surfaces from previous calculus courses, the quadratic surfaces, spheres, and planes. All those things are sketched in this section, so you want to go back and review those three sections. And then know this trick, if you put it into polar coordinates, you can sketch these things with a radial symmetry. Well, I did want to show you, here is the section on quadratic surfaces. There are 6 of them, so these are the ones you want to recall. When you see an equation that can be written as x squared over a squared plus y squared over b squared plus c squared over c squared, that's kind of hard to see looking at what equals 1, that's an ellipsoid. If you took its cross sections, say put z equals 0, look, that's an ellipse. X squared over a squared plus y squared over b squared equals 1. Maybe I should zoom that just a bit, huh? I'm going to lose some of these, but maybe it's worth it. Alright, and so that's an ellipsoid. Here's an elliptic cone. Z squared equals x squared over a squared plus y squared over b squared. When you recognize these equations, try and just have an idea how to sketch them. If you forget, you can use that method of traces. Intersect it with a plane, x, y, or z, one of the three equals a number, cut it and see if you, what kind of cut you get. If it's parabolas and hyperbolas, you say, oh, it's a hyperbolic paraboloid. The names give them away. The other things you want to know how to sketch, I'll put these up here, are spheres. Here's the standard equation for a sphere. X minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared. It's just the x squared plus y squared plus z squared equals r squared for a sphere at the origin. When you replace x by x minus x0, y by y minus y0, and z minus z0 by z minus z0, it moves it over, and x squared plus y squared plus z squared equals r squared is now this sphere with the same radius out at the point x0, y0, z0. And this is how we typically draw these things. Maybe you've seen this before in the last calculus. If it's radius r, you can draw a typical radius out here somewhere if you want. But you draw an equator of radius r, and you draw a circle in the plane. And so this is the cross-section this way, this is the cross-section this way. That looks sort of three-dimensional. And there's my sphere, this one. Planes are always like this: a number times x plus a number times y plus a number times z equals d. We call this a linear function equals d. Ax plus by plus cz equals d is a plane. You can find a point on it very easily by putting in two of these variables 0, and for instance, you get the point 0, 0, z equals d over c is one of the points on the plane. And then n, the normal to this, maybe you recall, is the coefficients of x, y, z. This will be a perpendicular vector to the plane with components A, B, and C. Finally, cylindrical surfaces. I just did an example here. If you get an easy plane curve like z equals y squared here, that's easy to draw. If x isn't present, then the surface is just that where x is arbitrary. So you slide it out here with x arbitrary, get parabolas, and this trough extends between plus and minus infinity in the x direction. It's just the union of all hyperbolas with arbitrary x and c equals y squared. So if you can draw these kind of things, you're ready to sketch all the sketches in there and then use a little radial symmetry occasionally. All right, so here's all of them. Try and look at their equations. A hyperbolic parabola z equals y squared over, x squared over y squared over b squared minus x squared over a squared, it says there. Here's a hyperbola of one sheet. It's just like the ellipsoid, but with one minus. A hyperbola of two sheets is like the ellipsoid, but with two minuses. All right, so they're very similar. You can kind of figure them out quickly. And here's the elliptic parabola we just did. All right, now let's go ahead with the next page here. All right, next problem here. Suppose I want to sketch f of x y equals 3x plus 2y. I know immediately that's a plane because of that equation. This is equivalently z equals 3x plus 2y. I write it equivalently. My double arrows meaning equivalent to, or has the same solution set. 3x plus 2y, and I have z over here, minus z, and add 6 over here equals 6. And here's my x plus by plus cz equals d plane. So I know it's a flat thing to draw. Now furthermore, I can find a point on it easily. I could put, for instance, x and y equals 0 and get z equals minus 6, or I could put y and z equals 0 and get x equals 2. Let's draw through the point 2, 0, 0 with normal vector 3, 2, minus 1. We can do that. And there it is. So to remember how to draw these, to draw the point 3, 2, minus 1, I'll go 3 on the x-axis, 2 over in the y direction, 1 down, and you'll notice I get a 3 by 2 by 1 box. I draw a little box, and then the opposite corner of the box is the point where 3, 2, minus 1 is. And so there's the normal vector, but I want to translate it over here to the point 2, 0, 0. Here's the point 2, 0, 0 on the plane. I draw the normal vector slid over here to the plane, and then I draw the plane perpendicular to that. I'm not expecting great drawings of these. I just want you to know to draw something flat and perpendicular to this direction, right? So, I'm not going to be picky on the drawings, but you want to be able to have an idea what's going on in your head. Einstein, a long time ago, said that imagination is more important than knowledge, right? If Einstein said that, it must be more important, right? So, I'm saying to you that being able to imagine what these look like is actually more important sometimes than being able to crunch all the numbers. So being able to picture these things and imagine what it looks like, and that will help you a lot on these problems. It helps you a lot to know what to do. Just like in Calculus 1, you need to be able to sketch lines, recognize a line, recognize a parabola, recognize a circle, and draw them. That really helped you to figure out how to sketch the areas to find that you're going to find. Similarly here, if you can draw the quadratic surfaces, the spheres, and the planes, that'll help you the rest of the semester. You recognize their equations. The quadratic surfaces are not as important, but you want to be able to do them. Now here's some more functions. Suppose I want to just find the domain of a function. Here's f of x, y equals 16 minus x squared minus y squared. What's square root of that? What is the domain? There's two things you need to worry about on algebraic expressions. Don't take any even roots and negatives, and don't do any divisions by 0. The rest of it is the domain. So I don't see any divisions here, but I do see a square root. The domain, I just demand that the argument of the square root be non-negative. So I demand that 16 minus x squared minus y squared be greater than or equal to 0. In other words, x squared plus y squared less than or equal to 16. Oh, what's that? I know what that is. By putting it equals 16, I get a circle of radius 4, and then less than or equal is the interior of the circle. So the domain is this region in the xy plane, right? Function of two variables, its domain is a plane region. This is the domain. You just set the argument of the square root to be non-negative. Now to sketch it, you try and get one of those tricky surfaces that we talked about. We notice if we square both sides, z squared equals 16 minus x squared minus y squared. And we arrange it, we get x squared plus y squared plus z squared equals 4 squared. Is a sphere, right? So that was our equation for the sphere. So I draw a sphere, except the square root means the non-negative numbers that have this square. So z can't be negative. So you square both sides, you throw out z negative, and actually what you have is a hemisphere. So I'm going to draw the hemisphere of radius 4, the top half of the sphere. And it has this domain underneath D that I drew over here. And now you can see why it has that domain. There's no points plotted except above this circle. That's disk, actually. The circle is the boundary, and the disk is the closed disk is the boundary with its interior, and the open disk, you leave this off. This is an important point, too. These points are included in the domain, so I drew them solid. If it was less than 16, I'd have to draw them dotted to indicate they're not in the domain. Here's an example here. F of x y equals square root 9 minus x squared over y squared minus 1, I should say. What's the domain of this function? I'm going to try and sketch it. It's not some standard function. I didn't say sketch here. But no divisions by 0, so I can't have y squared equals 1, which means y can't be plus or minus 1. So I'll draw dotted lines here, meaning leave these points out. Y equals 1, y equals minus 1 on the lines. Now I also don't want even roots of negative numbers, so I need 9 minus x squared greater than or equal to 0. Well, I solved that, and that means x between plus and minus 3. So I'll draw x between plus and minus 3 inclusive. I'll draw solid lines, and then I'll leave out these. It's this infinite strip here. Take away these two dotted lines. That's the domain of this one. So they're kind of tricky to graph, aren't they? And finally, here's another one. Suppose I had f of x y equals square root x plus y times natural log of 1 minus x squared minus y squared. If you have something besides an algebraic expression, which is arithmetic, powers, and roots, you can have an algebraic function like natural logarithm. Natural logarithm, you just have to take into account that those, you remember their domains. Natural logarithm is defined for its argument positive. So you demand that the argument of the logarithm be positive, right? And then you demand that the argument of the square root be positive, non-negative. And you have to take the intersection of those two things, right? Now the product is defined for any number, so you don't have to worry about the product. So we need the intersection of x plus y greater than or equal to 0, which is, how do you draw that? You draw x plus y equals 0, which is this line. And then what happens, since x plus y is a continuous function of x and y, one side of that line will be greater than 0 and the other will always be greater than 0 or less than 0, and the other side will always be greater than 0 or less than 0. For this kind of equation, it always turns out one side is greater than 0, one side is less. So you plug in your favorite test point, plug in 1, 0, something easy. 1 plus 0 is positive, so we know it's this side of the line. If I put in this point minus 1, 0, I'd get a negative number. That wouldn't be in the domain, so I know this is the wrong side to sketch this side. So that's how you figure this out. You draw the points where these are on these inequalities. You draw the points where they're equal. Check on each side, a test point on each side to see if that side satisfies the inequality. For a continuous function, if that one point satisfies, the whole side satisfies. And same thing over here. This one, I rewrite it as x squared plus y squared less than 1. Oh, wait a minute, that's the interior of the unit circle. So that's the open disk, actually. And I should have sketched it that way. I threw it backwards here. I need to fix it for the length. This should be a solid line because it includes equal, and this should have been dotted because it's supposed to be less than 1. So solid here and dotted here. And then you've got the domain of this function is what's inside in the unit disk on this side of the dotted line. Well, here's some here's some problems to look at out of this section. Try these and just get back used to sketching these things. Out of section 13.1, let's try these. Just turn in the answers, not the work, because to scan them and send them in is too much trouble. And too much trouble for me to read them. I can't read scans that carefully. So do 18, 20, 23 through 26, all of them, 34 through 44, the evens only out of this, and before the end of the day, Wednesday, send me those. Plus I'll assign 13.2 tomorrow to turn in.